Welcome to another fabulous day of Calculus 3. We're going to be taking a look at line integrals today, and there are three types. And I want you to know all three types. Now, in my lectures, I'm going to call them type 1, type 2, type 3. They don't call it that in a book anywhere, but just to make the distinction for each type. Okay, now the three types are very distinctive looking from each other, so you'll know which one you're doing at the moment you're given one or that you have to set it up. You'll know the application, but you kind of have to learn all the ground rules for each type of line integral. So a line integral is not your regular integral, okay? It looks like a regular integral though, but it's got a whole different set of rules and regulations that go along with it, okay? So here we go. Before we get started on line integrals, you have to know how to parameterize curves, because that's one of the key things or part of the ground rules for doing a line integral, because you're actually not integrating over a line, you're integrating over a curve. So you have to be pretty well versed with curves. So if you're lucky enough to be handed a curve already given to you as a vector valued function, that's great. You don't have to parameterize. But a lot of times they don't give you the curve like that. So it's your job to go parameterize it. And we have discussed parameterizing in the first, say, month of this course, but you may not have done it for a while. So we'll revisit it. So far, you know these kinds of integrals here. This is Calc 1 and 2. Calc 1 and 2. And what are you integrating over? You're integrating over an interval. What do you mean? Well, you know, like when somebody goes, hey, there's the function y equals f of x, yay. And, you know, we want you to integrate going from a to b, yay. So what you're integrating over is this interval going from a to b. That's what you're integrating over. Okay, I get it now, fine. What about a double integral? You've seen those now, you've done a few. What are you integrating over? You're integrating over R, a region, typically in the XY plane. What about a triple integral? Oof, we've done some of those. Yeah. What are you integrating over there? You're integrating over Q, a solid. So now we're going to do line integrals, which really should be called curve integrals, but you know, they just named it line integrals. I don't know. They're another class of integrals that are needed in vector calculus. Okay, and we're going to integrate scalar functions or vector fields along curves. That's what a line integral is. Now, because the line integrals are integrated over piecewise smooth curves, you may be responsible for parameterizing these curves. So let's look at a parameterization that's kind of cool. And they talk here about smooth curves. Smooth curves are ones that don't have sharp corners or cusps. Let's parameterize a piecewise smooth curve. So there's going to be sharp corners here, but for each part of the pieces, we'll have a different parameterization. So check out this curve. This curve C is equal to C1 plus C2 plus C3. So it's got some parts. So the journey, there's three legs to the journey. So curve 1 starts at 0, 0, 0, and you can see this arrow here, and it ends up over here at 0, 2, 0. So we're going to have to parameterize C1. We'll do that in a moment. The second leg of the journey starts here at 0, 2, 0, and they call it C2, and ends up at 1, 2, 0. So we're going to have to parameterize that second leg of the journey. And then finally, we're going to strap on a jetpack here and shoot off of the earth straight up vertically, starting at the point 1, 2, 0 and ending at 1, 2, 1. And that's going to be denoted C3. Okay, so let's parameterize each in turn. C1. Now, when you parameterize, your parameterization has to not only include the vector valued function, you have to give the range of time where that vector valued function is moving, if you will. And when you plug in your endpoints for the time, they better match the endpoints of your journey. Otherwise, that parameterization is not legit. And so let's say you, by accident, got a parameterization where the final answer matched what it was supposed to be, I won't give you any credit for pure luck. So C1, what do we know about it? It starts at 0, 0, 0, and it finishes at the point 0, 2, 0. So I'm going to call the vector valued function for it R1 of t. I hope you notice that we're on a straight line here, and that the x coordinates stay 0 the whole time on the whole journey. So we're just going to put a 0 there for the x component. And further, since we're traveling along the y-axis, z is also zeroed out. So the z component for this vector valued function will also just stay 0 the whole time. Does that always happen? No, it doesn't always happen. But for this particular curve or line, it does. Now, what is varying? It looks like the y coordinate is changing up. So how about if we just pick a variable, we're going to call it t, that's our parameter, and we'll let y be t. And we're done, except we have to talk about what is the range of t for this line segment, so that we start at the point 0, 0, 0 and end up at 0, 2, 0. Well, I claim that if we start t at 0 seconds, that will definitely start us at 0, 0, 0, if you substitute that in your vector valued function. And if we finish at time equals 2 seconds, then we'll definitely finish at 0, 2, 0, and I'm done. Now, parameterization is not unique. So you could have picked another alternate parameterization that, as long as it matched the curve, it's still legit. Okay? I'll do another alternate one in a moment, but let me just go with this one. So now let's move to the second leg of the journey, C2. Okay, I'm going to call the vector valued function R2 of t for this second leg of the journey. What do we know about this journey? You start at the point 0, 2, 0, and then you travel along a straight line that stays in the xy plane the whole time and ends up at the point 1, 2, 0. It looks like the z coordinate stays 0 the whole time, which it does in the xy plane. So we can safely put a 0 in the z component slot. And it looks like the y coordinate stays at 2 the whole time, because we're traveling parallel to the z axis. So y stays at 2 the whole time. And it looks like x is the one that's changing. So how about if we let x be t? Now we need to specify what the range of t is to match this curve. And it looks like if I start t at 0 seconds, that will start me at the point 0, 2, 0 if I substitute that in the vector valued function. And if I finish when t is 1 second, that will definitely end me at the point 1, 2, 0 if I plug a 1 second into this vector valued function. Okay, we're done parameterizing the second curve. Done. Third curve, C3. We'll call it R3. Oops, I wanted to do pink. So R3 of t. Notice that for R3, we start at the point 1, 2, 0, but we have to finish at the point 1, 2, 1. And we're basically shooting straight up. Straight up. It looks like the x coordinate stays 1 the whole time. And so that'll be a 1. Y coordinate stays 2. And z is variable. So we'll put him as the t, and then t will start at 0 seconds and finish at 1 second. And I'm done. And this parameterization for this entire journey works perfectly. I want to show you a different parameterization. So I'm going to start over. And the reason why I'm doing this is some books, when they show you a similar example of a journey that takes more than one leg of the journey, like this one did, they prefer if the time doesn't always get reset back to 0 every time. So I want you to notice that every time I parameterize each of the legs of our journey, that my time, I just reset him to back start at 0 every time. And you know what? I'm the boss. When I'm parameterizing, I can do that. And I'm going to let you do that. Totally okay. Much easier also. Oh, way easier to do it that way. But I want you to see a different and alternate way to parameterize this same curve made up of 3 lines, because it works and it's perfectly legit. It wouldn't be the way I would do it, but I want you to see that it's just as good. And if you understand this, when there are alternate answers, you'll see why they're okay. So the first one, R1 of t, could have been parameterized 0, 2t, 0. Oh, okay. But then the time interval would be 0 to 1 second instead of the way mine is, in order for it to begin at 0, 0, 0 and stop at 0, 2, 0. So if you plug in these endpoints for time, I'm sure you'll see it matches. Totally legit. Well, which one is better? That the one you did first or this one? Does not matter. Pick your favorite. Okay, how about R2 of t? Now, folks, I'm giving vector valued functions for straight lines. I hope you remember that when we were going over lines and planes in space, and if you had 2 points, you could easily, get the vector that would describe, the direction vector. Do you remember getting a direction vector? Anybody remember getting a direction vector for a line in space? Yep. Yeah, and you remember, so you could go x, y, z equals, and you could parameterize or give the parametric equations for a straight line by simply, using your, this would be what, 1, 0, 0, and then pick one of these points on here. Let's say for C2, I wanted to pick the point 1, 2, 0, and then use 1, 0, 0 as my direction vector. So that would work also. You can easily parameterize a line in space doing it that way. That's fine. Don't forget that. Just wanted a little reminder. But I'm not going to do the R2 like that for the second time around. So what I'm going to do is, this one textbook doesn't like to reset the clock back to 0 every time. They want the clock to pick up where you left off from the last leg of the journey. Why? I don't know. They just like to roll like that. So what if we said, okay, for this second curve here, C2, we want to have time start where we left off from the last leg of the journey. So you got to start at 1 second. Oh, man. Well, it looks like you're still going to have the y and z coordinates stay constant the whole time. Fine. And then it's still the x that's changing. But if we have to start it at t equals 1 second, how about we let the x component be t minus 1? And that way, when you plug in the 1 second here, it'll start where at the 0 for the x coordinate. Yeah, that works. And then when does it finish? Well, we need the thing to finish when x is 1. So if I let us have 2 seconds be the stopping point for the time, and I plug a 2 in here, 2 minus 1 does give me a 1. So it matches. So that works. And then finally, for the third leg of the journey, again, this one textbook wanted to start the time where we left off from the last leg. Okay. Well, since we're shooting straight up, and it looks like the x and y components were constant the whole way at 1 and 2 respectively, and then z is the one that's changing, and if we're starting at 2 seconds, how about t minus 2 be the z component, and if you plug in 2 seconds there, it will start at z equals 0, and then we'll finish at 3 seconds so that the z coordinate ends up being a 1. Okay, and this alternate way of parameterizing is totally legit. Okay, now you're ready for type 1 line integral. This first type of line integral can only really be used in one application, and that is when you're finding the mass of a wire. Yeah, and the alternate name of this kind of line integral is known as a scalar line integral, because you're going to be taking the integral of a density function that is a scalar function, and it doesn't involve vector fields at all. So type 1 no vector fields get involved. And you're probably thinking, yeah, so what? Well, the other two types of line integrals that we're going to be covering, both of those deal with vector fields. This one has nothing to do with a vector field. That being said, let's take a look. This is just a penumbra of a proof here for the derivation. So here's your wire, and okay, cut it up into little pieces, partitioning it up into little end sub arcs of wire. And then the length of the ith sub arc, so just pick your favorite little chunk there of sub arc, is delta s sub I. Remember, little s was arc length, and we did arc length a couple of modules ago. And it's important that you kind of remember that because it's coming up. So I think we should do just a quick review of the arc length formula, because this is super important for line integrals. So if you'll recall, if you've got a 2D curve, let's say given by r of t is equal to x of t, y of t, then, and somebody says, well, hey, I want you to find the arc length between time equals a seconds and time equals b seconds. The arc length, which is denoted little s, that's tradition in every book, is the integral from a to b of the magnitude of the velocity vector, aka speed. Does anybody remember this?
Yep, completely.
Good. Now, if you have a 3D vector field, sure, we did that too. So let's say you had some weird curve here in space given by r of t is equal to x of t, y of t, z of t, and somebody said, hey, I want to know the arc length between t equals a and, say, over here, t equals b. Fine. Arc length is denoted little s. It is still going to be the integral of speed, the magnitude of r prime, except this radical will involve the sum of the squares of the three components. This is all review, and I'm doing it for a reason. Okay, arc length. Back to our wire. So if the length of each subarc is small, then the total mass of the wire can be approximated the sum of all the little masses of all the little subarcs. So you're going to have a sigma, I going from 1 to n, f evaluated at an arbitrary point inside of your little subarc of a wire, f evaluated at x sub I, y sub I, z sub I, in other words, times the little length of subarc there. And then tighten up the partition and let the norm of the partition, which is the norm is the length of the longest subarc, have that approach 0. The limit is going to approach the mass of the wire. So here's the definition of the line integral, taking a limit. So you've got f defined on a region, it's a smooth curve of finite length. Then the line integral of c along of f along c is, and I'll give you the 2D version and the 3D version so you can handle both. When you're looking at a line integral, you're going to see an integral symbol, just like Calc 1 or Calc 2. But then you're going to see an uppercase C located at the bottom of the integral symbol. And that is a nice way of denoting that it is a line integral and not one of those regular integrals from your Calculus 1 and Calculus 2 days. And then you'll see the density function, and then ds, not dx. This is ds. So make a little note for yourself, because I will dock you points if you accidentally put dx there. ds, it's a little arc length element. And that is the limit as the norm of the partition goes to 0 of this Riemann sum, if you will. And then the 3D version for line integral, you got your integral symbol with a C. You'll have some density function, which is a function of 3 variables, ds, not dx. There's no I anywhere in here. You're going to have lim as the norm of the partition goes to 0. I is just an arbitrary index you're using for your sigma. And if you recall, you used I probably a lot in your calculus 2 days for the index of your sum. It's not imaginary. We don't deal in imaginary in this class. So I, in another context, would mean a complex number imaginary, but not here. Now, these line integrals, as it stands right here, are not integrable. Like, do not try to integrate one of those right there. You got to do some work. You got to turn it into a regular integral. Well, what are the ground rules for that? We're going to go over that right now, the big theorem. So please pay attention, otherwise you won't be able to do a line integral. So let's do a 2D version first. If you're given your vector valued function with components x of t, y of t, the arc length element, the ds that you see in this line integral is essentially replaced with the magnitude of r prime dt. In other words, you're going to have the square root of the sum of the squares of the velocity vector times dt. So you're going to integrate with respect to the parameter dt. And a similar formula holds for your space curve. So the big theorem, this is how you turn a line integral into a regular integral that you can actually evaluate. So we'll do the 2D and then the 3D. So you've got f, that's continuous on some curve you've got. And you can think of this as being the density function, because these line integrals, essentially, you're finding mass of a wire. So you've got your vector valued function. You've got time going between a seconds and b seconds. Your line integral, which will probably have this kind of look to it, you're going to replace it with a regular integral, the kind you learned in Calculus 1 and Calculus 2, except the f of xy, you have to replace x. You're not allowed to have any x's or y's here. You're going to replace x with the x component that you'll cherry pick off of the vector valued function. And then the y will get replaced with the y component from the vector valued function. And then you'll have ds is the arc length element. This is the arc length element. And that's going to be replaced with what we just went over. The arc length element is that big old radical with the sum of the squares of the velocity vector in there. So you're going to have to take some derivatives. dt. Now, hopefully this is integrable, because sometimes when you've got an integrand with a whole yucky radical like that in there, it might not be integrable. You might have to whip out your calculator and use one of the definite integral features on there. Now, if you have a 3-dimensional curve and they ask you to do a line integral, no problem. You can do one. Yeah, I'm having some problems with my Word documents here. So here you're going to integrate between a and b, and your f, you'll have to replace your x's, y's, and z's with the x's, y's, and z components from your vector valued function. Yeah, you got to do a lot of replacements. And your arc length element, so here's your arc length element here, is that huge radical, because now you've got to worry about 3 components here that you take the derivatives of, square them, and then add the squares together, and you integrate with respect to t. Not x, not y, t. And hope that's integrable. Okay, so if you're ready, I'm going to do a couple, and then you're going to try one. Okay? You think you're up for that? Maybe? Maybe. All right, I'm going to start off easy, and then it'll get harder and harder. So each one has a different flavor to it. So when I do these lecture note examples, please keep in mind that all of the different types and flavors, you're responsible for each and every one. And you'll see all the different flavors when you do your homework and so on. Yeah. And I may put the different flavors on a quiz. So they want us to evaluate that line integral, x plus 2 ds. ds. S is arc length. S, as in sugar, stands for arc length. And they're giving you the vector value curve, and they're giving you the time. Oh, nice. So you don't have to parameterize anything. That was very sweet of them. Now, the first thing that you better do is you better find R prime, because you're going to have to use that arc length element, which involves the magnitude of R prime. So you better go do that first. So you know how to find R prime because we did that in a module a couple months back. Derivative of t is 1. The derivative of 4/3 t to the 3/2 is 4/3 times 3/2 times t to the 1/2. The derivative of 1/2 t squared is 1/2 times 2t. And let's clean this up, reducing. And a little bit of reducing here. Didn't hurt anybody. And there is our derivative. Yay. So now if we look at the magnitude of R prime, just to clean that up, you're going to take the radical of the sum of the squares of the components. So that's not going to look too pretty. Yuck. I think I'm forgetting something here. There's a 2.
Yeah, I was about to say it's 2t.
Thank you.
Yeah.
Forgot my 2. And then let's see here. Once I square everything, I get 1 plus 4t plus t squared. Okay, so let's just save that for the moment. So now if you take a look at this line integral, and I know it's a line integral because it's got a c down here underneath the integral symbol. That's how we know, ooh, it's a line integral, not just one of those regular integrals. So that means you got work to do. So you're going to integrate from time going from 0 to 2 because they told us, okay? The x plus 2 needs replacements. I don't want to see the letter x in your line integral. The only variable I should see is t. So what do you replace x with? You look at your vector valued function, and whatever the x component is, this one's kind of easy. You replace x with the x component from your vector valued function. This one is just t. It's usually never that easy. And then plus 2. And then ds stands for arc length element. So the arc length element is going to involve this big square root times dt, because we're going to integrate with respect to t. Now, this integral at first glance looks horrible, like, oh my God, am I going to even be able to integrate this mess? And it turns out the power rule with u substitution will work. Believe it or not, check it out. I'm going to let u be equal to everything under the radical, the t squared plus the 4t plus the 1. Okay, then what would du be? Well, the derivative of t squared plus 4t plus 1 is 2t plus 4 dt. Well, how's that helpful? Wait a minute, hold on, hold everything. If I factor out a 2, I get 2 times t plus 2 dt. Why is that so cool? Because good news, I got good news. There already is a t plus 2 dt in the integrand waiting to get swallowed up and serve his role as the du portion. Yeah, exciting. So what's the only thing I'm missing? Oh, bummer. I need a factor of 2. But hey, it's just a constant. I can easily put a 2 in there, provided I multiply the front by its reciprocal. And now I have all my ingredients. My du is totally there. So this integral looks like 1/2 the integral of square root of u du, which is 1/2 the integral of u to the half. And then using my power rule, that's 1/2 times 2/3 u to the 3/2. And then I can do a little bit of simplifying and then back substitute my u, which I know it wasn't pretty, 1 plus 4t plus t squared, yuck. And then I'm going to evaluate this antiderivative between the limits. Yikes, okay. Substitute your 2 first. I'm going to keep the 1/3 out in front. So I have 1 plus 4 times 2 plus 2 squared to the 3/2. Minus, and then substitute the 0. Be careful because it doesn't always go to 0. And then what do I get here? I get a 1/3 times, oh, this is not going to be pretty, 1 plus 8 plus 4. Yikes, 13 to the 3/2 minus 1 to the 3/2. Yeah, one extra step. 13 to the 3/2 is the same as 13 square root of 13, and 1 to the 3/2 is simplifies to 1, and there we have it. That's the exact answer. The approximate answer, if you whip out a calculator, is 15.29. Now, these scalar line integrals traditionally should always be positive because they do represent the mass of a wire. Now, some textbooks have these crazy homework problems where it ends up where it's a negative answer, and I just get kind of upset with that because in the real world, for a scalar line integral, that'll never happen. Now, the other kind of line integrals, because they represent something else, they're going to be working with vector fields. You can get 0 as an answer, negative numbers as an answer, positive. But this first type, you shouldn't. Okay, so there's your first line integral example. Not too bad, right? Not too bad. All right, let's take a look at another one where it's not parameterized. We're going to have to do the work. So they want us to evaluate this line integral, x squared minus y plus 3z ds, where c is the line integral shown. Okay. And notice it's a line segment between 0, 0, 0 and 1, 2, 1. And folks, you know how to parameterize a straight line because the direction vector, you know, is just going to be, you know, terminal minus initial, terminal minus initial, terminal minus initial. And then you can pick the point 0, 0, 0, and you can get the parametric equations, you know, 0 plus 1 times t, 0 plus 2 times t, 0 plus 1 times t. And then you can put this into a vector valued function, r of t, t, 2t, t. And then the only thing that's missing from this parameterization is what are the start and stop times from your t. So if you'll notice here, if I let time begin at 0 seconds, that'll start me at 0, 0, 0. That looks like it works. And if I let time end at 1 second, that will, after I substitute into this vector value function, that will finish me at 1, 2, 1. So this is the parameterization for that curve that works fine. Remember, parameterization is not unique. You may come up with an alternate parameterization for this little line segment, but it better work, better not just be any numbers you pull out of the air. It has to start at 0, 0, 0 and stop at the point 1, 2, 1. And then it's okay. Okay, so I spoke too fast. There's a little mistake I made here. 2 minus 0 there. 1 minus 0, 2 minus 0, 1 minus 0. And you should get 1, 2, 1. So now we parameterize the curve. Great. Now what? Well, you're not done. I might give you 1 point out of 20 if you got that far. Well, I parameterized the curve though. I know, 1 point out of 20. You got a lot of work to do. What else? You got to evaluate the line integral. Come on. Parameterizing the curve, that's easy peasy. Do the work. Okay, so what do we have to do? So we're going to essentially find the mass of this wire. The wire is a straight line. And they gave us a density function in the integrand. It's x squared minus y plus 3z. So that line integral, I'm just going to copy it down here, becomes, oops, that's a 3z, ds becomes the integral time going from 0 to 1. Well, why is time going from 0 to 1? Because when we parameterized it, we said what the time is going from. That's part of the parameterization. You miss out on that, I dock you a lot of points. You have to tell me the range of your time that your parameterization is corresponding to. Okay, then what? You have to rewrite your density function. You're not allowed to have x's, y's, and z's in your line integral. You're only allowed to have the variable t. So x is going to be replaced with t, the x component from your vector valued function. So x squared is going to become t squared minus y. Well, what does y become? The y component from your vector valued function is 2t. So replace your y with 2t plus 3z. This z gets replaced with the z component from your vector valued function, which also happens to be a t. And then you're not done because this ds is an arc length element. Oh no. So we better go get r prime. Now this is not too bad because r prime for our straight line is going to be a constant vector, 1, 2, 1. And so the magnitude of r prime, which is the square root of the sum of the squares of the components, just turns out to be square root of 6. So the arc length element will become square root of 6 dt. That's kind of nice when your arc length element involves a constant. And this square root of 6 can be pulled out in front. This is just a multiple. And then another thing I'm going to do before I integrate is I'm going to combine like terms, make it easier for me. Negative 2t added to 3t is just t, so that's a little cleaner. And so this is an easy calculus 1 integral, and my antiderivative is t squared over 3 plus t squared over 2. And when I evaluate between the limits, I will get square root of 6 multiplied by the sum of 1/3 and 1/2. And that's square root of 6 times 5, 6. Final answer, 5 square root of 6 over 6. So please note, the value of the line integral does not depend on parameterization. So in other words, let's say you parameterized your curve a little differently than me, but it was still a legitimate parameterization. Would your line integral value result be the same as mine? Yep, it will. So don't worry. And that's the end of that example. So you guys are all working on letter D. You're distributing the scalar first, avoiding problems. And your mass is going to be given by the line integral of the density function ds. Okay, so try this on your own. Oh, shoot, thank you. I forgot. Thanks for reminding me to record. My apologies for those of you watching at home. We were doing this nice mass of a spring problem. So we found the velocity vector there. Then we got the magnitude of the velocity vector to help us get the arc length element. And after doing some arithmetic, it turns out that the magnitude of the velocity vector was 1. So when we set up the mass as a line integral, we substitute in place of z, the z component from our vector valued function, which turned out to be t over square root of 2. The arc length element is 1 dt. And this is an easy integral to integrate, right? Calculus 1 type stuff. So this term here, if you do the math, I get 18 over square root of 2. I don't usually rationalize my denominators. So if you want to, you can, but I'm done. Okay, this is approximately 144.47. Okay, any questions on that one? Is everybody okay? Not too bad? Okay, for the grand finale, I want to do this last one for you, and this will wrap up the scalar line integral stuff. So next week, we're going to be looking at the two other types of line integrals that involve vector fields. So this one's hard because the fact is that this curve has two parts to it. The curve is C1, and that's a union symbol. C1 union C2. Ooh. Now, C1, the first leg of the journey, starts at 0, 0, and ends up at the point 1, 1 along a straight line, y equals x. So that's the first part of the curve. The second leg of the journey is going to start at 1, 1, and it's going to go back to the point 0, 0, but not along the same path as we went. It's going to go along the parabola. Okay, so your C2 is along y equals x squared. So this is a hard problem, and watch closely. Yes, this is the kind of stuff I put on exams and quizzes. It's the parameterization that's going to get you. So we're going to parameterize, and it's going to turn out we have to actually take this line integral, and we're going to actually have to do two separate integrals. Wait, what? Yeah. You're going to first do the line integral along C1 and do all the work that involves that. And then you're going to add to that a completely separate line integral along the other leg of the journey, curve 2. There's no way out. Got to do it separately. So let's parameterize C1. Well, how do we do that? Well, I'll call it R1 of t. You want a vector valued function, and then you want to tell me what the limits of time are. I don't know. What am I going to do? Well, it's a straight line, and it is a function of x. And I taught you how to do that. So when you have a function of x, you go, hey, just let x be t. Ha-ha. And then y is equal to x, so y is equal to t. Ha-ha. And then the time interval for t, we want it to start at the point 0, 0. So how about let time start at 0 seconds? Easy peasy. And then we end up at 1, 1. So how about if we let time stop at 1 second? Perfect. So now R1 prime is 1, 1, and you need R1 prime because we're going to need the magnitude of the derivative to get our arc length element. And so that's square root of 2. So that's really not too bad. We've got a constant there. So the C1 x ds is going to be a regular integral going from time 0 to 1. And then the x ds, no, you don't put x ds there. X, you're going to use the x component that you'll cherry pick off of your vector valued function. ds is the arc length element, so square root of 2 dt. And so this is pretty easy to integrate because it's going to just have t squared over 2 going between the limits of 0 and 1. And so we'll get square root of 2 over 2. Let's save this for later. Now what? You got to go along the other curve. And this one's the hard part. Why? Because when you're doing a scalar line integral, you're not allowed to start at time equals 0. Okay. You can't have time go backwards. It's going to be kind of tricky. So C2, let's parameterize. So here's what you're not going to want to do. You're not going to go, oh, we have a function of x. So I'll call this R2 of t. Let's just let x be t, and then y is t squared, and then t will go between 0 and 1. No, this won't work. Well, why not? Because when I plug in t equals 0, I get the point 0, 0. Well, I don't see what the problem with that is. Well, here's the problem. This curve has to begin at the point 1, 1 and go along a curve and finish at the point 0, 0. So if you try to parameterize this curve in the way I just showed here, this parameterization, starts at 0, 0 and ends at 1, 1. No bueno. Well, what am I going to do? You got to start over. So this is the trick. Since I want to start at the point 1, 1, how about if I let x be 1 minus t, and then since y equals x squared, y will be 1 minus t, the quantity squared. Now when I let t go between 0 seconds and 1 seconds, this matches the curve. Check it out. When you substitute t equals 0 into this vector valued function, try it. You actually get the correct starting point, which is 1, 1. Yay! And then when you plug in the ending time value of 1 second, substitute that into this vector valued function, you do end up with 0, 0. And that's perfect because you have to end up at the point 0, 0. So this is the parameterization. I know that was kind of weird, but that's how we roll. And now I'm going to go get R2 prime. And R2 prime, the derivative of 1 minus t is negative 1. I don't know why this is moving around. And then the derivative of 1 minus t, the quantity squared, using the chain rule, is 2 times 1 minus t to the 1 power times negative 1. And you can move this negative over here like this. And I could distribute the negative 2, but I'm not going to. You'll see why in a minute. When I get the magnitude of this derivative, I get this mess. Don't try to FOIL it out or anything. Leave it. I know it looks disgusting. Just go with it. So now this x ds over the curve, what's that supposed to be a C2? We're doing this over C2. We'll go time going from 0 to 1. The x gets replaced with 1 minus t because that's the x component from our vector valued function. The ds is the arc length element, and this is key that you get ds stands for arc length element, and it's this horrific looking radical dt. Oh my God, is this even going to be integrable? Yes, watch. This, believe it or not, is integrable using the power rule. Let u be the radicand. I know, this is looking terrible. And then du, using the chain rule, is 8 times 1 minus t to the 1 times negative 1, which is really negative 8 times 1 minus t. Good news and bad news. Good news, there already is a 1 minus t dt in the integrand. The only thing that is missing from my du is the factor of negative 8. But if I put in a multiple of negative 8 and then multiply the reciprocal, I'm good. And so now this is just one of these power rule problems, which we all have seen a lot of times. So go ahead and integrate using the power rule. And then let's see, I'll clean this up a little bit. And then I'll back substitute for u. Oh man, I better leave myself a lot more room because my u was this 1 plus 4 1 minus t squared. Woo! And then when I evaluate this between 0 and 1, oh my, I'll pull the 1/12 out. When I substitute a 1 in there, this ends up being 1 to the 3/2. And when I substitute a 0 in there, oof, I know. This ends up being 5 to the 3/2. I know, pretty disgusting. And then you have this negative 1/12. And remember, this is 5 square root of 5. Okay, so what's our final answer? And for this problem, so we could be finished with this line integral. It's just nuts. So final answer. I know, like, wow, this is crazy. You're gonna first get the first line integral I did. Where the heck is it? The square root of 2/2 that I said save for later. That was going along the first leg of the journey. Plus this -112, I know, 1 minus 5 square root of 5. Wow, that looks horrible. I know, it looks pretty gross. If you punch this up into the calculator, it is a positive result, which is good because these are usually mass of a wire type problems. So I get 1.56. So, whew, yeah, it's pretty gross. So that basically concludes this lecture. So now you've seen your very first crack at the line integrals. Congratulations.